This is Race McCord with a video presentation of my final project for EELE 465 Advanced Microcontrollers. And this device here in my garage, which it's about 20 degrees out right now, is a spring smasher. So to introduce what it does, is it just has a normal on-off switch because it has a 12-volt battery. And then from the 12-volt battery, it runs just a DC motor. And then on top of the system, it has a 5,000-pound load cell that if I pull on it a little bit, it shows 17, 18 pounds. I let up 0 pounds. That's calibrated in its own unit. And then off the side, we have a capacitive measuring device. And it measures 36 inches. So how this device would normally work is you go in and you put a shock absorber from the bottom to the top post, and we have a little toggle switch that runs the motor up and down off the 12 volts. It's a very slow motor, but it loads up to about 3,500 pounds, is as much as we have loaded up to. The motor is rated for more, and the load cell is rated for 5,000 pounds. So the objective of this project was to use a microcontroller to accurately control the system and have the motor run to a desired set point. Because before, you'd have to come over to the toggle switch and run it where you wanted it, and there used to be a display from the measuring device that would tell you where you're at, and you'd have to manually jog it up and down. And it wasn't the most precise thing, because there was always human error, and there was always a little bit difference every time, so I wanted to make it concise every time, and you only run to about 7 to 12 set points consistently with your shock absorbers. So to do that, what I've used is an MSP 430 FR2355 microcontroller here. Here's breadboarded. It just has several switches. And then from the MSP, I have a an SPI display that we use in class, LCD display. And also off the MSP 430, I have 3 lines to my motor control board, which is rated for 24 volts and 20 amps, which is enough to run this board. And it just has 3 wires. It has a ground, a PWM output, and a directional bit. And then also hooked up to my microcontroller is I have 5 different push buttons that when the design is done, they would mount on the machine, because there's 2 of them that would be limit switches, another one that would be a zeroing switch, that when the motors ran down, it would hit the zeroing switch and re-zero the distance. And then there's also one for command to zero the machine, and then there's also one to run to the set point. And those just run off of hardware interrupts. And also what I have connected here is a 16 position rotary switch that acts on an interrupt too. So when it changes, actually changes the set point of the system. And then off of that, all I have here is just a powering board, just 3.3 volts from my 110 to 12 volt converter down to 3.3. In the final system, it'll take 12 volts and have its own voltage regulator. And then also on my board, I have 4 lines running to my measuring device. It's a 21-bit capacitive touch measuring device, and the clock signal is actually supplied by the MSP 430. It runs about 9600 baud, and so it takes samples. So that's basically everything that's laid out. And to summarize, mainly make sure I don't forget anything, we have the motor control board, which is just a ground and 2 bits controlling it. We have 5 different toggle switches, 2 of them for limit switches. One of them is a command to zero the device. The other one would be mounted up to the device, so when it hits it, it knows where it's at. And that would be done anytime it wants to be calibrated by the user or on startup. And then I have a push button that actually tells it to go to set point. And I also have an SPI LCD display hooked up. And that should be it. And my measuring device, my 21-bit measuring device, that works very similar to UART, but slightly different. So now let's do a demonstration on how it works. So right now, we have a distance of 25.087. So on a certain push button, I have to zero it. And by zeroing it, it would assume that it's above the set point, because the set point is going to be the bottommost position. So it's always going to want to run down and find the toggle switch that tells it where it's at. In this case, I'm going to run it up a little bit. And when I hit the button to zero it, it's just going to run the motor down until it hits this push button theoretically. So that's the zeroing one. So the user would be like, oh, I want to zero it, it's off. The motor would run itself down until it hit this other toggle switch at the bottom of the stroke, and then it'd reset itself. Here I just have it reset itself at 26 inches exactly. The motor does overshoot from when the command is sent, or I just have my measuring device is not permanently mounted, it has a little wiggle in it. And as you can tell, me by touching it, it wiggles it 3/100ths of an inch. But once it's more hard mounted and I do a little bit more tweaking with the motor overshoot, I can get that value very low. But we're looking for a tolerance of 1/32, which this is a lot smaller. So my set point's 25, and the user would come over here, use this toggle switch, set it to 25. I want it to go there. So I'm ready to go. I have my device in. I'm going to say go to 25. The motor's going to go up. And then it's going to stop when it hits 25, which in this case, it gets within 1/100th of an inch, which is well within tolerance for the system. And when the devices are more hard mounted and a little bit more tuning goes into it, that number can get lower. And also to verify it goes down, if I change my set point to 27, I hit the button the user is going to use, go down. It's going to go down. And this time, error is less than 1/100th of an inch. And then also, to prove that it works, when all my push button switches are mounted, when the system's more finished, there's limit switches to make sure that you're not going to try to overrun the motor. The motor board does have protection, but the manual toggle switch does not have any protection that limits the motor. And I don't know if the motor's protected internally, but I just don't want to, run anything up to the top or to the bottom. You can damage components. So if I change my set point to something, let's say, above this, so it's just, I'm going to hit go, and it's just going to run up. And if I had my push button set, say it hits the top of its stroke, I want it to stop, it's going to hit its push button, and it kills it where it's at. So then at that point, you need user interference to pull her back down or reset your controller, which would be coming down and hitting the bottom where it re-zeroes itself to the resting position, which is the bottom of the stroke. And that's about everything for the project. I do not think I forgot anything. Like I said, it needs a little tweaking. It needs everything hard mounted. It needs PCB actually designed and made for all these wires. But overall, all the code's done, all the testing, all the bugs worked out. Just needs a little bit of optimization on the finished product, and that's done. That's all I have.